Hello and good morning. My name is Muhammad Afiq Hakimi bin Zuhari. My matric number is 2501967. So right now I want to present about the lab report about the OPAMP. So the first is the objective. The objective to understand the basic characteristic of operational amplifier circuit configuration, to compare the theoretical experimental simulation values in each configuration, to determine the effect of capacitor bypass resistor and internal operational amplifier offset voltage to the output voltage. We utilize the LM741 OM model powered by the power supply. The supply is 15 volt for all the three simulations using the sine wave input for the circuit 1, the inverting amplifier, with the input resistor R1 kilo ohm and the feedback resistor R2 10 kilo ohm. We observe a clean sine wave output. The key trend was an amplification and an inversion of the input signal. The circuit 2, the voltage follower. This configuration uses direct feedback, resulting in unity gain. The observed trend was that the output waveform exactly followed the input, demonstrating its high impedance buffer. The third circuit, the schematic trigger, when the utilizing positive feedback with the R1 1 kilo ohm and R2 33 kilo ohm, the observed trend was the conversion of the analog sine wave input into a digital like square wave, sharply switching between saturation voltage. The result and analysis after 1 until 2 minutes, the simulation result showed good agreement with our theoretical expectation. For the inverting amplifier, the expected gain was AV R2 by R1 negative 10, and the observed output peak closely matched this. Similarly, the voltage follower demonstrated an exact match with the expected unity of gain positive 1. Confirming its ideal buffer function, the schematic trigger successfully produced the expected square wave, validating its function as high hysteresis comparator. However, we did observe minor deviations that are critical to analyze using principles-based reasoning. Firstly, the output amplitude in the inverting amplifier was slightly less than the calculated 10 peak. This is explained by the non-ideal characteristic of the output saturation voltage, where the OM cannot reach full 50 volt supplies rail. Secondly, the edges of the square wave from the schematic trigger were not perfectly vertical. This phenomenon is caused by the OM slew rate constraint, which limits the maximum rate at which the output voltage can change. Finally, a key constraint identified is the inherent trend of the inverting amplifier, where achieving a high predictable gain comes at the cost of a low input impedance determined directly by R1. Familiarity with principle-based approach after 1 until 2 minutes. Our interpretation of this result is fundamentally guided by core electronic principle, specifically the OM2 golden rules in the inverting amplifier and voltage follower negative feedback. The virtual short principle is the cause that allows us to apply Kirchhoff current law (KCL) at the inverting node. The effect of this is the precise calculable gain formula. Conversely, the schematic trigger uses positive feedback, which is the cause of disabling the virtual short. The effect is that the OM lock to a supply rail, creating the invertesis required for clean noise immune voltage compression, a fundamental concept in analog to digital conversion circuit. This approach ensures our findings are technically justified, not merely observational. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ifan bin Halim. My matrix number is 251091614. Now I will focusing about the analyze the integrator amplifier. The operational amplifier integrator is a circuit performs the mathematical operation of integration where is the output voltage is proportional to the time integral of the input voltage. This is achieved by placing a capacitor in the feedback path and resistor at the input. Its primary function is to transform a square wave input into a triangular wave output, or a step function into a ramp output. A critical non-ideal characteristic is its susceptibility DC offset voltage drift, where any small DC voltage like the operational amplifier internal offset is continuously integrated, causing the output to quickly ramp towards the supply rails. To stabilize the circuit, a large resistor like the 10 meg is placed in parallel with the feedback capacitor to limit the DC gain and provide a stable operation point, although this sacrifices some accuracy at very low frequencies. The operational amplifier differentiator is the inverse circuit, performing the mathematical operation of differentiation, where the output is proportional to the rate of change of the input voltage. Its configuration swaps the integrator's component, placing the capacitor in the input and the resistor in the feedback path. It transforms a triangular wave input into a square wave output. The main non-ideal challenge for the differentiator is noise and instability, because its gain is proportional to frequency. It has very high gain at high frequencies. The characteristic amplify any high frequency noise or sudden transient, potentially driving the circuit into oscillation or saturation. A small resistor is often placed in series with the input capacitor to limit the high frequency gain and improve stabilities. For the conclusion, the laboratory experiment effectively achieved its objective by characterizing 5 key operational amplifier configuration and comparing their theoretical performance against simulated results, simultaneously highlighting critical non-ideal effects. Specifically, the non-inverting amplifier and the differentiator confirmed their respective gain and derivative equation operating linearly, while the inverting amplifier clearly demonstrated the practical limitation of voltage clipping due to being restricted by the power supply rails. Furthermore, the experiments illustrated the necessary addition of compensation component, a large feedback resistor in the integrator to prevent DC offset saturation, and a small feedback capacitor in the differentiator to ensure high frequency stability by limiting noise amplification, thus providing a comprehensive understanding of both ideal and real-world operational amplifier behavior. That's all from us. Thank you so much.